Hi everyone, this is Burak Aslan and today I will be talking about engineering energy transfer from 0 dimension to 2 dimensions. I would like to acknowledge support from TÜBİTAK and Boğaziçi University. And let's start with exciton in two-dimensional materials. Excitons dominate the optical spectra in two-dimensional materials. And because of that, people have closely inspected them. And tuning the excitons have been important for applications as well as for fundamental study. And it's possible to create excitons in 0 dimensions as well. And in this case, the 0 dimension is the quantum dot. Quantum dots are artificial structures. They can be made into semiconductors with some band gap. We can create excitons in them and they can exhibit photoluminescence. And it's possible to engineer their band gap by engineering their structure of core, shell, and the constituent atoms. They can also possess high quantum yield, which can reach up to 100%. The excitons also exhibit long lifetime before they recombine. Now, the thing is, what happens if we bring the two dimensions together, if we place quantum dots on two-dimensional materials? I said that quantum dots possess high fluorescence quantum yield, but that actually depends on the environment. For instance, if you place quantum dots on a molar of molybdenum disulfide, as in this case, their photoluminescence will be strongly quenched. In this case, we are not looking at an optical image. This is actually a wide field PL image of quantum dots placed everywhere on this plot, and we see strong photoluminescence except on this triangle on which a monolayer MOS2 lies. So what happens is, basically, what happens that results in this quenching is actually non-radiative energy transfer from the quantum dots to the two-dimensional material. What happens is, first we excite our material, our quantum dot with light, and we create excitons in them. Normally there will be high PL yield, but the excitons have long lifetime of nanoseconds, and they transport to the 2D material before they can radiate. Next, when the excitons are in the two-dimensional material, the two-dimensional materials have low quantum yield, less than 1% or even 0.1%. So the radiation is lost, the excitons cannot recombine radiatively, so as a result we lose our PL that would occur if there was no substrate, if there was no two-dimensional material underneath the quantum dot. So that is called a non-radiative energy transfer. So that's an example of a non-radiative energy transfer. And that non-radiative energy transfer depends on the spectral overlap between the emission of the quantum dot and the dielectric function of your acceptor. Since our acceptor is very thin, the non-radiative energy transfer rate is dominated by the absorptivity of the two-dimensional material and the emissivity of the quantum dot. So if we can engineer somehow the dielectric function or the absorptivity of our two-dimensional material, we can engineer the non-radiative energy transfer between the two. And one of the ways is actually to apply strain to your two-dimensional material. We can use strain because these two-dimensional materials are very strong. They can endure very large strain even compared to their bulk counterparts. And people have used this technique for various purposes, such as for band gap engineering or for achieving indirect to direct band gap transition, for instance in bilayer WSE2, and for various purposes. So we can use that technique, and one of the simple ways is to get a flexible substrate and place your two-dimensional material on top. So if you bend that substrate, you can apply in situ strain and probe optically at the same time. And if we place quantum dots on the two-dimensional material, the quantum dots will not get strained. What will happen is the two-dimensional material will get strained. So its optical response will change, which will eventually change the interaction between the two dimensions, between the two-dimensional material and the zero-dimensional quantum dot. Let's take monolayer WS2 because its line width is already very good and it doesn't change much. It doesn't change as much as it changes in monolayer WS2. So let's, and what we do is we start with it because it has the smallest line width within this family of two-dimensional materials, and its line width is relatively insensitive to strain. So, to be able to calculate the strain-dependent dielectric function of monolayer WS2, we represent its dielectric function as a sum of Lorentzians. So, one Lorentzian per transition, per exciton or per feature. And here I am talking about the in-plane dielectric function. So we fit it to the sum of 4 Lorentzians. This is the imaginary part, and if you use the same dielectric function, it can fit the real part fairly accurately as well. There's some mismatch nearby the C and D features, but that's not important because we will be interested in the A exciton region. So let's compute the strain-dependent dielectric function of WS2, and we obtain the out-of-plane dielectric function from literature, and we don't expect any change, and there's no change expected under strain. And what happens is A, B, C, D features shift with strain, so the in-plane dielectric function will be affected. We take the rate of shifts from the literature from our earlier measurements. That way we can compute the strain-dependent sum of those 4 Lorentzians, and we can compute the strain-dependent in-plane dielectric function of monolayer WS2. And this is the real part, and that's the imaginary part calculated for various strain levels. So the main thing that happens is A and B features redshift with increasing strain. So now we can compute the strain-dependent interaction between these two material systems. Our model is that we use a radiating dipole model interacting with a lossy thin film, which is a two-dimensional material. So the dielectric function of the 2D material is as known, and there's an interplay of screening by the two-dimensional material and absorption by the two-dimensional material of the quantum dot radiation. We will see that it's basically dominated by the absorption part. So the non-radiative energy transfer rate is proportional to this integral where E is the electric field of the emission and epsilon is the dielectric function of the two-dimensional system, and we integrate this over the whole volume of the two-dimensional material. And we can represent this normalized to the dipole radiation into space without the two-dimensional material. So this is the normalized n-ret rate between the donor, which is the quantum dot, and the acceptor with respect to the dipole radiation into vacuum. And here Ke is the emission wave number, P is the dipole moment, and E is the electric field, V is the volume, as I mentioned. And just a simple schematic, if we can tune the interaction such perfectly, then we could tune what we want, which is the non-radiative energy transfer. But the reality is not as perfect because the quantum dot emissions cannot be so narrow in that red region. So quantum dot emission is broad, and if you take an example such as this one, the line width, the full width half maximum is larger than 80 millieV. So if you look at the calculated rate and plot the photoluminescence of our quantum dot, this is how it would look like. As you see, the exciton dominates the non-radiative energy transfer rate because the absorption is more dominant. And you can if you multiply the two, so if you multiply the PL with this emission rate, with the transfer rate, we'll get the net non-radiative energy transfer. So we will be getting rid of this normalization. So as you see, with increasing strain, the response changes. So you get the maximum transfer when the strain is around 0%, and it is slightly smaller when the strain is negative, meaning there is compressive strain, and if you increase the strain, that rate will decrease. So if you compute this area underneath of these red to blue curves, and plot that as a function of strain, this is what we will obtain. So around 0% the rate is maximum, and that rate decreases with increasing strain, or it will decrease with compressive strain on the left hand side. The tuning factor is only around 4, so it's not that large, because we are limited to the line width of the quantum dots. When the quantum dot line width is large, this is the best we can get. So larger factors will be possible if we had narrow quantum dot emission. Graphene is semi-metallic and there is no excitons, and we don't expect any changes with strain, so that's why that can be used as a control sample. There is only some energy dependence because of the dipole term here, but there is no strain dependent other than that. To summarize, we can use strain as a means of tuning two-dimensional materials, and we can tune the non-radiative energy transfer rate between quantum dots and two-dimensional materials, but only a factor of 3 to 4 is expected, and high-quality quantum dots will help. And this is a result for a different kind of quantum dot, so that's why it looks different, and the factor was 3 for this calculation. Thank you very much for your attendance, and we hope to follow with the experiments.